Hi. In a couple of previous videos, we've reviewed a lot of information about optimization. But in economic applications, we were also talking about the properties of total cost function. And to be exact, short-run total cost function. Okay, today we're gonna do something new, because as it turns out, there is a function that works very well in terms of demonstrating the behavior of short-run total cost function. And that function is the one that you see over here. This is a cubic function. However, look, as you see, I define this function in terms of q, of course taken to the power of 0, 1, 2, and 3, and 4 coefficients. Now, what we are going to do today is we're going to examine under which values of those coefficients this function can actually approximate to us how the actual total cost function behaves. However, before we move on to actual calculations, we need to set down some general properties of the total cost function. So look, in the short run, total cost function can be divided into two parts: variable cost and fixed cost. As I thought, you probably know very well from microeconomics, fixed cost is the part of the total cost that do not depend on the level of production, right? If you have a company, doesn't matter if you produce 7 cars, 17, 20 or 50, you still need to pay your accountant, pay your lawyer, and pay the cleaning services, right? So this is the part of the cost that does not depend on the level of production. However, remember, this is true only in the short run, because in the long run, all costs are variable. Okay, and now, when we look at the graph, we can easily locate fixed costs, right? This is the part that does not depend on the level of production, right? So we will have this level of a cost even if we will produce 0, right? Variable cost, on the other part, is the part that does depend on the level of production. If we want to produce more cars, we need to hire more people, we need more materials, we need more machines, right? So this is the first distinction we need to make, right? Now, so where can we find fixed cost? Well, of course, this is the cost the company endures when level of production is at 0. So fixed cost must be over here. And from here, we can get the first property of this cubic total cost function that it should possess. And this property is fixed cost must be positive. We are assuming that this is a short run, so at least part of the cost must be positive. Okay, and look, our cost function, this means that if we have our cost function, so when we produce 0 units, our cost is equal to fixed cost. And this fixed cost should be positive, right? Okay, let's check it out for our total cost function. If I'm going to plug in 0 here, I'm going to have A times 0 to the power of 3 plus B times 0 to the power of 2 plus C times 0 plus D. And look, all those expressions are zeros. So all we get here is D. Look, if I compare those two expressions, I'm getting that fixed fixed cost is simply equal to D, and from this we get our first restriction, and the restriction is that D must be positive. And look, in this graph, I could just easily replace fixed cost with D, and everything works, assuming all other constraints or other constraints are also fulfilled. Okay, now let's get to the second most important property, and it's also very simple. Total cost must be must be increasing and is defined only for positive levels of production, so only for positive Q. Of course, with the obvious exception of fixed cost. Okay, now this is also telling us a lot. Look, economic theory tells us that total cost, short-term total cost function is shaped like this. So it starts at some D, it's increasing, but slower than proportionally. So first it's concave, then we go through inflection point, it becomes convex, and starts to increase faster and faster, so faster than proportion. So we definitely know that this function is always increasing. Now, how can we make sure that C is increasing? What mathematical expression could tell us the same thing? Right? The fact that C is always increasing, so total cost is always getting bigger with the level of production, is simply telling us that the slope of total cost is always positive. What measures the slope of total cost? Well, the slope of total cost is measured by first derivative. First derivative is marginal cost. And marginal cost, in this case, must be positive. Okay, so let's calculate marginal cost for this case. So marginal cost is simply first derivative of total cost with respect to quantity. So we now take the total cost function and we differentiate it with respect to quantity. We get that this is 3AQ squared plus 2BQ plus C. Okay, and now let's look at a very simple thing. Let's notice what type of function is that, right? We went from cubic function, which we differentiated once, so this is a quadratic function, right? So the graph for it, it's a parabola. And now is the first question. If this is our short-run total cost, then how should look marginal cost? Look, what do we know? It is a parabola. And we need to make sure that this parabola is always positive. Now look, if the parabola would have its hands down, we could not maintain this assumption, right? The only way that this parabola will have, will always be positive if we assume that it has ends up. So out of this, out of the condition that this must be positive, we get our first conclusion. A must be positive only if A is positive parabola will have ends up. So from this we get a second restriction on the parameters. So we know that A must be bigger than 0. Okay, so look, but however, this is not enough. Now, what do we know for now is that the parabola will have ends up. However, look, this parabola could turn up here or here. And both of these situations are the problem. In the first case, well, even if this parabola would be above 0, we would have a negative q over here. So negative q, we need to rule out. And the second possibility is that parabola has ends up. It's defined only for positive q in our case. However, the minimum of it is below. And actually not only minimum, but a lot of points. This is impossible, right? Because if we have a negative first derivative, it means that the function on the top has an increasing part, which we ruled out. We said the more you produce, the higher the cost. Not unit cost, but the higher the total cost. And okay, so look, what do we see over here? And look, how does this is associated with our parabola? Look, here the function is increasing but slower and slower, which means it has positive slope, but this slope is getting smaller and smaller and smaller. So if derivative measures slope, it means that the function must be steep at the beginning, but it's getting flatter and flatter and flatter. And exactly at this point, at the inflection point, this parabola gets a minimum. We remember that at the minimum, the slope of the parabola is 0, just like in the case of the polynomial function over here with inflection point. And look, what happens then? The function starts to increase faster and faster and faster, which means that its slope is increasing. So, now, what can we say about this particular point? Well, this situation here is a little bit problematic. In a way, we need to assure two things. First, this q here that gives us the minimum of marginal cost needs to be positive, right? We know this because we cannot have negative levels of production. The second thing is that MC, marginal cost at minimum, also need to be positive. But look, we already have all the tools to deal with this case. All we need to do is to find minimum of the marginal cost and make sure that this marginal cost is given for positive q's and is positive itself. So look, now what I'm going to do is to find minimum of marginal cost. So I'm differentiating marginal cost with respect to q. So I'm differentiating this with respect to q. I'm getting that this is 6aq plus 2b. And I equalize it with 0. So look, out of this, I'm getting that 6aq is equal to negative b, or q is equal to negative b over 3a. Okay, now what we have already established is that a must be bigger than 0. So look, now the next thing we need to establish is what is going to be b. Now look, if a is positive, we've got minus in front. The only way this expression is going to be positive is if b is smaller than 0. And this is how we get our third restriction. So now we need to just make sure that minimum of marginal cost is above 0. So what do we need to do is simply to substitute the answer we've got into the formula for marginal cost. So marginal cost minimum is equal simply to marginal cost out of negative b over 3a. Right? This is our formula for marginal cost. So look, what I'm going to do now is I'm going to substitute this value, right, into the formula, and I'm going to see what I'm getting. Okay, so this is 3a times negative b over 3a squared plus 2b times negative b over 3a and plus c. Okay, first thing we need to do over here is to calculate it all, right? And put it into common denominator. So look, out of this we get that this is b squared over 3a, right? Because this would be 3a squared, and we have 3a up front, they cancel each other out, so we've got b squared over 3a. Then we add to it, and actually we subtract, 2b squared over 3a. And now I also need to put this into common denominator with everything else. So now I will have plus 3ac over 3a. Okay, now if I calculate it all out, we see that out of this I'm going to get negative b squared. So this is equal to b squared minus 3ac over 3a. Now this needs to be positive. Oh my god, I'm sorry. Of course, the other way around. 3ac minus b squared. Now, we already know that a is bigger than 0, right? So denominator is already bigger than 0. But what we need to have now is the numerator is bigger than 0. So what we get out of it is that 3ac must be bigger than b squared. However, look, for this to be bigger than b squared, c must be positive because 3 and 8 are positive. To be bigger than something that is positive, c Now we know all the restrictions that need to be imposed on the short run total cost function to be proper. So to work intact with the predictions of economic theory. So look, we can write that C of Q equal to AQ to the power of 3 plus BQ squared plus CQ plus D is a proper short run total cost function if. Now, if A is bigger than 0 and B needs to be smaller than 0, C needs to be bigger than 0, D needs to be bigger than 0, and 3AC needs to be bigger than B squared. If those conditions are fulfilled, we have a proper short-run total cost function. And look, let's just do one example to see how it works. So we've got a cost function given by 1 over 3 q to the power of 3 minus 7q squared plus 111q plus 50. And the question is this a proper total cost function? Look, we can check it simply by looking at those restrictions. We don't need to go through this entire process once again. So look, we see that A equals to 1 over 3, bigger than 0, very good. B equals to negative 7, smaller than 0, very good. C equals to 111, bigger than 0, good. What the way it's supposed to be. And our D, so fixed cost is equal to 50, and it's also bigger than 0. So, 1, 2, 3, 4. 4 conditions fulfilled, 1 more to go. So now, what is 3AC? 3AC is 3 times 1 over 3 times 111 is 111. We need to make sure that this is bigger than B squared. Now, B squared is simply negative 7 squared. So this is 49. And we see that it is actually smaller than 111. So, makes perfect sense. This actually is showing us that this cubic function is a proper short-run cost function. Okay, this is enough for this week. The next week, we're going to start Maclaurin and Tyler series. See you in the next video.